Right, good morning, everyone. Let me start with thanks to the organizers and the invitation to give a seminar talk over here. My name is Feng Wei Yan. I'm a postdoc in University of Sussex, working with Annotate and Vanessa in the scientific computing group. This talk, also thanks to the funding bodies for the funding the research. This talk is quite different from the previous ones. It will be heavily focused on the computational side of things. So, and that is what I do. I have a background in computing, in engineering side of things, and I do quite a lot of parallel programming with fast numerical methods, and that's the method called multigrid, and I'm gonna talk about today in detail, and I'll give some applications in the end. Well, one more thing to say on these slides, the motivation. I think motivation is quite straightforward, so I didn't even bother to put on this separate slide. We have partial differential equation models, and once we got the models, we want the solution. How could we get a solution as efficient as possible? And that is the motivation. Also, that's a very big statement to say partial differential equations, because that contains a lot of different types. And let me narrow it a little bit, and let's look at parabolic systems, and in particular some phase field or phase field-like systems. And well, one of the things may be debatable. Using finite difference is quite efficient for phase field methods. They are also finite elements used, but in a 3D situation, you might have to deal with large mesh files, and that's why it's not making it as efficient as finite difference. So that's the choice why use finite difference, because the aim is phase field models or phase field-like models. Now, the second point is, well, need some discussion, because that's, maybe you are familiar or maybe not. In parallel computing, explicit methods are the ones that's very favorable in a sense for getting a very high scalability in big cluster. But then they have a downside for the explicit, where you have to use a very small time steps for the complicated systems, and sometimes it might not be possible if we look at a problem like the so-called stiff problem. And this is a binary alloy certification in 3D, coupled with a time-dependent temperature, and that is the novelty in the model published there. We scaled up to 1,000 cores for the simulation in the previous national supercomputer. And this model, the temperature, the diffusional temperature or the transmission of temperature is in seconds, if I remember, in that sort of time scale. But if you imagine that little seeds in the liquid, and suddenly the solidification starts, that time scale is very, very fast. It's beyond seconds. And that creates a very different time scales. And that's sometimes called the multi-scale problem. In those problems, if you use explicit methods, the delta t would be extremely small to deal with that. And that's why we say it might not be possible to do. Hence, the implicit schemes, there is a family methods called PDEs, backward differential formulas. If we do decide to use that, hence the third point, explicit, we don't have anything to solve. It's just a simple update at each time step. But if we decide to use implicit methods, we have an algebraic system rising at each implicit time step, and we need to solve that system. And the choice of the method solving that system would have a huge influence to the efficiency we gain in the end. And they are simple ones where, like Jacobian Gauss et al., I will talk about later on, will normally have order bigger of n squared. The one we're going to give in detail, multigrid. In linear case, proving with a linear complexity. Non-linear case, haven't really got a proof, but from practical point of view, it's linear complexity, something I'm going to show later on, how we get that. Having a efficient method is still not enough. We want the robustness even more, and hence the last 3 points. Mesh refinement, that can be said suitable for all, pretty much all phase field methods. Or I have an example for this later on. Adaptive time stepping is something quite problem specific. Some problem might not be suitable for it. Some problem will be extremely suitable for it, and we will have one of the case later on as well. And we want to solve the system in parallel for more efficiency. So that's the objectives we're going to do. The outline is the first part, hopefully we'll complete in about 30 minutes or so, with a description of multigrid, linear and non-linear in detail. And then we look at a very simple thin film model from Gaskell. Model is in 2D, it's relatively easy, and but it got pretty much all the things I want to talk about for the advanced techniques like adaptive mesh refinements and adaptive time stepping. It's really just a very good example to show how those techniques would work, and we will have a look at the evaluation of those techniques. Because if you've got efficiency, but if you lose a lot of accuracy, or you get something completely different, then really it's not worth doing. So accuracy is what matters. And then in the end, we'll look at some, it's quite computational demanding and memory hungry optimal control problem in 2D and 3D for whole cell tracking as the application, which is linked to the main theme of the workshop. Right. Talking about multigrid, I have to start with Jacobian Gauss-Seidel-like iteration methods. They are at the core of multigrid, and I would regard multigrid as just a way of speeding up Jacobi or Gauss-Seidel. They are very well-known methods. You can list a lot of things about them in a few minutes. One of the things very important, and what the multigrid really exploits on, is the smoothing property. And what do I mean by that is if the problem have a high frequency of error, generally Gauss-Seidel would smooth that out to the high frequency of error very, very quickly. But it will do very bad if only the low frequency remains in the problem. So what you normally see using a Gauss-Seidel or Jacobi to solve a problem, if we're looking at the residual of the problem, you would say a rapid convergence to start with, where the high frequency of error was in the system, and then a very slow convergence with a lot of iteration. That's because it's not robust on the low frequency of error. But then think about the definition of frequency. It is to do also related to the grid points we're using. So what it means is if a low frequency on a very fine grid, if we translate, or if we somehow translate that solution to a coarser grid, where the grid has less grid points, some part of that error will become high frequency, or have a high frequency, and the Gauss-Seidel and Jacobi will do pretty well. That is the idea about the multigrid. We solve the high frequency, we literally deal with the high frequency on the finest grid, and then restrict that solution where the sum of the solution would have a high frequency on a coarser grid. Deal with that and do it again until we reach the coarsest grid, which would have the least grid number. And to deal with the low frequency of error on the coarser grid, it would be easy because the extreme low computational cost. We can do a lot of iterations with little increased time. So that is the idea. And then you could have a update, because when you get the solution on the course grid, you can take that as update to the final grid until the correction reaches the finest grid, and that's the solution we want. And that is a standard multi-grid V cycle. And there are other cycle strategies, but this one is the one you will see in parallel setting probably most of the time. Reason is, well, I'll discuss the reason in a few moments. Right. Having said a general idea about the multi-grid methods, we can look at in details. Our talk allowed me to actually go into details of those and see how the multi-grid will really do. Giving a very, to start with the example, let's take a linear case. We've got a linear problem. A is a linear matrix. U as the true solution to the problem. B is the right-hand side. We are using an iterative method, so can't really get to U. And let's say V is this approximated solution. We can have a true error obtained in this way, equation 2. We can calculate the residual at any given time we want using the approximated solution, and it should be no difficulty to see the relation between the error and the residual. But the thing is, to obtain the true error is as hard as to obtain the true solution in the first place. So we look at the next best thing would be approximated error. That is what happens if we take two grids and do a V cycle. Computes the approximate solution, residual, do the restriction, although there are quite a lot of restriction schemes, depends on the type of grid points you use. Some type of grid points like vertex centered, you can use injection, which is very easy. It takes the corresponding value of that point. Some, which you probably will see later on, is called a cell-centered grid, where there's no corresponding points exist between the consecutive grids, and something have to do that. But you can use, you take an average between the surrounding points. That's called a full weighting. Anyhow, that is a way to do it, and you got the solution on the course grid, which that is the restricted residual, and you can compute approximated error with the restricted residual that's solved on the final grid. And this error would form a correction term once it's interpolated back. Also, there's a lot of scheme to do the interpolation as well. And the next update would improve the solution on the fine grid. So that is the linear multi-grid in two-grid case. Non-linear multi-grid somehow is a bit, well, it will be slightly different, because one of the things that we really rely on in linear case is error equation, but this error equation doesn't exist in non-linear case. So we have to think about something else. There is one of the scheme called the FAS, full approximation schemes, that's saying, well, once we restrict the residual, we can also restrict the solution we compute on the fine grid. So what we do in the nonlinear case is include a modified right-hand side, and that's just a play around with the numerics. If the V is a true solution to the nonlinear problem, this would be 0, the term, but it won't be because of the iterative methods we're using. Anyway, it should be very easy to see how we form a coarse grid problem by using a restricted residual and a restricted solution that we computed on fine grid, and then we can compute the solution on the coarse grid, VC. Sorry, the notation F is fine grid and C is coarse grid. I hope it's self-explanatory. And then compute the error in a way which is similar to the linear case, interpolate the error and do the correction again. So that is the same as a linear case. And that is a non-linear multigrid with FAS scheme. I do have got quite a lot of problems. Once I reach 6, I think it's something I haven't really thought about in a presentation, haven't really discussed in detail, is, well, in first place, how do I solve a non-linear problem with the Gauss et al? So, I think I should elaborate on that a little bit more. We are using what are called a pointwise smoother. So it's different from using a full Newton method where you globally linearize the problem. This one, we linearize the problem at the spot, at each grid point, and solve the nonlinear problem. If we write the nonlinear problem in this and V as the approximated solution, we can somehow rewritten it just to make notation easy. And then the update should be quite straightforward, where that is the derivative with respect to Vij on that grid point. So that's you can see how it relates very Newton-like, but then they do have some subtle differences. This one is worked on the pointwise.
Question?
Yes.
So doesn't your derivative actually couple grid points? So you have it at V of I comma j, but in fact, if you do a finite difference or some other approximation to that Jacobian, it's going to couple the grid points.
You wouldn't know the derivative is just with respect to at one particular point that we're going to update. With 5-point stencil, it will involve other 4 points, but we're not looking at other 4 points. We're not coupling with other 4 points. No, to take the derivative. So with a Poisson-like equation, if we do that, oh sorry, Poisson would be linear, would it? So probably not a good case to give. But anyway, we can talk about that a bit later. Well, one of the good things with using this pointwise equation is we can pretty much do what we like to the grid, because as long as you provide, we are using 5-point stencil, let's make it clear, and as long as you provide whatever the 5 stencil wants, like one over here, I know this could be quite overwhelming to start looking at, but thinking about this is just a left-hand side corner, left bottom left corner of the grid point, and that is quite a lot of grid points in there. As long as we have a Gauss cell layer to mirror the corresponding points on the adjacent block, we can do 5-point stencil at every internal grid points, and that grid pointwise smoother would enable us to freely distribute the workload, and now we're getting to the parallel and adaptive meshing side of things. So maybe I should say first that parallel is through domain decomposition, where we cut out domain into little boxes. Sorry, I haven't mentioned that to start with. And with the Gauss cell update, with pointwise update and the Gauss cell provided and updated accordingly, should be able to do that very, very efficiently. And also, we'll be able to do adaptive mesh refinement really easily, because the smoother doesn't see the whole structure of the grid. But one of the things I think I need to say is it's a workshop talk, so I think it's a good to lay out the problem we are having in my field at least, and hope there might be solutions and interesting discussions in the end. So they are very big problems in the parallel scaling ability, at least in geometric multigrid, which is the one I'm talking about. If you think about each of the little blocks as I showed previously as this mesh block, okay, to distribute the workload over here through a domain decomposition should be fairly easy. You've got lots of blocks, say, for the sake of argument, you got 64 computational units, and it should be fairly easy to say, well, probably each one would have 1 or 2 blocks to work on, and that's good. The problem now really is come down to the courses grid, where you only got 4 units or 4 blocks to distribute, and if you got 64 cores, 60 of them will remain having nothing or no work to do at this stage. And the V-cycle I described before is a very sequential order, and a very strict sequential order. You couldn't really parallelize that order, so you have to have going down in a sequential as a sequential list. So that's what gave the biggest challenge on the course grid. But now that's not even my point. My point is, well, some of you might say, well, could you not use a finer courses grid? But the point is, if we look back at here, the courses grid, as I described, is a one to deal with a low frequency error, and hence will need quite a lot of iterations for Gauss-Seidel to actually get rid of the low frequency. So if you use a very fine course grid, you have to use a lot numbers of iteration, and that increase of iteration is not linear as the unknowns on that grid. So in the end, you might be able to use a very fine course grid, but you won't risk. You probably will improve the scalability because you got a lot more work to distribute. But in the total computational time, you might be worse off, and that is a trade-off for this multigrid method in parallel. And it is what we've seen in practice. The alloy certification we did. We scale up to 1,000 cores, and if we do that, goes beyond, and we see negative efficiency gain, and that is, we believe that is caused by the choice of the courses grid. Possible solutions, yes, they are. Non-linear problem will be difficult to converge, but linear problem should be easy. So if we use a full Newton method to start with, when we solve a non-linear problem, we first use a full Newton to linearize the problem globally, and then you would only have a linear problem to worry about. Hence, this grid can be quite fine. But the difficulty of doing that also, we would call it Newton multigrid, but it's a method is a bit understudied right now. Some of the numericals have been compared and studied, but how to do adaptive grid with Newton multigrid, especially considering the grid is nested together, might be difficult. So it would be quite a nice project for becoming students to do, I think. Maybe also something to bear in mind. There are solutions to this, and there are also some engineering solutions to this. How do we distribute the grid in a cluster to make sure that it won't go too bad? But there will be a problem to worry about every time you use a multigrid in this way. So, and that's it. How am I doing with time? Okay, should be fine. Now we come to the first of the two model of the day, droplet spreading model from the thin film approximation. That is a simplification from the Navier-Stokes, where we take assumption that there is no flow contribution perpendicular to the substrate. With that assumption, meaning the thickness of flow have to be very, very small, and hence the name thin film, and also the velocity of the flow will be very slow as well. So the I think I just suddenly forgot the name, but I'll come back to me. So we're looking at a liquid like a silicon oil or honey. So the ones that moves very, very slow, and that is a droplet spreading model. Two equations coupled together. H is the height of that droplet, H naught is the initial height. And the P is the internal pressure, but also exists on the full domain. BO is a Bond number. We're not really having that in this situation because the plant is horizontal. If you have with this alpha, if you have inclined plane, they will come into play. This term is called a disjoining pressure term. It's acted on the moving contact line to make it more realistic, and also having this equilibrium angle to simulate the surface tension. So how? Because you don't really see the if it's on a metal plate, you don't see the droplet disappear. But if it becomes something like wood, it might disappear, which becomes a wetting problem, and that is a term to deal with that. But in the case we just gonna do over here, quite simple. It is just assume it's not a wetting problem. It's just a droplet spreading for a bit. The difficulty over here really is the moving contact line. Thinking about the initial condition, what we assume the initial condition would be is like if you have a droplet between your finger and you lift up the finger, and at the very moment where the droplet lifts the upper finger, that's the initial condition. And that's the initial condition is saying the droplet should be very tall, and the moving contact line over here, the angle is nearly 90 degrees. So that is why the difficulty comes in to simulate that. And if the angle, because once you smooth it, it turns out to go underneath and come back. So initially you would require a very small time step, because with that initial condition it's very difficult initially. But once it starts to spread, the angle will become small. The whole shape of the droplet will be very smooth, and hence you can use a very large time step. And that is the reason why using adaptive time stepping will be very suitable for this problem. Also the adaptive mesh refinement, because although it's not phase field, but it does have a touch of the phase field there. That's the moving contact line is what we really want to resolve. And once that's resolved, the model should be fine. So what we should really do is concentrate all our points on this moving contact line and resolve it as accurate as possible. So that bit would be a ring shaping 2D would be the one we're focusing the mesh points on, and hence the adaptive mesh. Just to summarize the solver, and then I won't need to repeat it again for the later models. We take the second order finite difference, which is 5-point stencil. The whole software is built on a mesh called a paramesh. You might have heard of this. For the mesh generation, the AMR, we use BDF2 method with adaptive time stepping. Also something I had to say now, coming back to these orders of the schemes. To gain efficiency solving partial differential equations. The branch I'm working down today is how do we do the computation fast. Also another branch can be combined both as well, is to take the higher order schemes where the error would, where the solution would converge much faster. What we have done, although not going to present it today, is the obtaining the overall second order for this problem and for some phase field problem as well. But that's something I think it's different, so won't be here in this talk. But that's why it's having the orders of the schemes. I think it is to do with how do you get solution efficiently. AMLET variation of FAS is the ones that allow us to use adaptive mesh refinement with the multigrid. It's not too It's not too complicated, but I'd rather not to go to too much detail into the multigrid. Coming back to the smoother, I said, I demonstrated the one beforehand, but that's with one variable. So if you you've got two variables coupled together, what you normally do would be solve this equation on all grid points and then solving P on all grid points again, or maybe solving that one on grid points first and then solving P on the same points again. But we find doing that would have a quite big restriction on the time step you can take. So what we do is a coupled update like this. And for this particular problem, comparing to the one I described before, using this update with coupled together, updating two variables simultaneously on each grid points allows a dt to be increased by roughly a factor of 1,000. So it does have quite big difference, although that's maybe problem specific. I'm not aware of any analysis on this, how the stability region of two different update scheme in a sense. Essentially it's just a same really update, but update scheme is different. Okay, we have full weighting restriction by linear interpolation if someone wants to know, and parallel through domain decomposition. That's what I said. So I think over here for this model, the idea for having this model is to evaluate we are getting the answer we wanted. So and also this very simple problem, and there's a lot of details and results in the literature. Over here we do a comparison. That is the initial height of the droplet, and once you let the droplet go, it will diffuse and spread, and the height of the droplet will decrease. And that is the one we've got. There are some subtle differences in between, and we believe it's because we do have a second order convergency over here, where Gaskell didn't do a convergency test in that paper, so we won't be able to know which order of convergency they have, but look like first order. But give you a quantitative comparison, a good comparison with the that's showing that we are getting the quantitative similar results. By doing that results, we can also recall the computational cost for each one. That's our 5 grid. Go up to, I think, 1,020. No, actually, that's a 2,000 squared. We can plot the time required for each time step using multigrid against a line of slope of 1. And we see in this nonlinear case, we do have a linear complexity over here. And why we have this linear complexity is because if you look in each time step for the algebraic system, if you look at the residual every time you do one V cycle, the rate of error going down is pretty much parallel with a different grid, and that is what we expect from multigrid, because we'd assume that the error is independent of grid size, and that because of this feature, multigrid is linear complexity. And I'm not exactly sure how they get something like this. Maybe they haven't really got to the point, and once it's coming out to complex, but no, I'm speculating. But we are doing okay over here. So that is the residual with V-cycle parallel. We can show a adaptive mesh refinement. What I wanted to show actually is a dynamic adaptive mesh refinement, which means we refine and coarsen the mesh on the fly as we compute the solution. Initially, the droplet is very tall and in the middle, where this red region represent the finest resolution we can have, and I believe in this simulation it's 1024 squared. If refined everywhere, it would have that resolution, but clearly it won't be having that many grid points. Yellow one is one level coarsen, 512 squared, and then 256 and 128 squared. Once we let the droplet spread, we can see the ring of the highest region. Well, the parts of them were refined as the moving contact line moved, and the part of them will coarsen, because once you out of that moving contact region, you have a much smoother solution where you don't need that fine grid.
But is this progresses the interior of your surface is not changing? You don't need the mesh that's inside the bulk of.
Exactly. What was?
Do you?
No, we don't have any equation or anything going on inside.
Still, you have quite refined mesh.
Yes, but I think if you really let it go, it will be coarsened over here. But it's down to the choice of this of the refinement. So you can make that choice very conservative, where you have to refine a lot of points, where you can make it very aggressive, where you coarsen a lot of parts. So in this case, we're not really coarsen in the middle, but I suspect, we'll show a video over here actually. I suspect as it goes. I think this one runs longer than the one showed on the picture. So yeah, as it goes, this one will be coarsened.
Right.
So that's a simulation of a droplet spreading. Sorry about the squashing of the trying to get into the frame. Adaptive time stepping, as I said, it's really it's just problem specific, this method, but for this particular problem it works very well. Mind you, the sudden drop is because we want it to finish at this particular time so we can do the comparison. So that's why we use a bit less of the delta t. But that is the evolution of the delta t we take from 0 to 10 to the minus 5. And each time we're allowed to go up a bit. For this adaptive time step, a lot of research is done for the error estimate. OMA is doing quite a lot of stuff on that. But the one we're using over here is a very engineering solution. So if we look at the number of V cycles to see whether they converge, whether it failed to converge, whether it nearly failed to converge, and to give an indication whether we should reduce the time step, whether we should increase delta t. It seems it's working so far from the grid.
Is it always in a linear fashion that it is increased?
Depends on how you increase that. Normally it would increase by a percentage or over the old delta t. I think it's increased by a factor of 10. Sorry, a factor of 10% every time it increases. So, but then you can give that different values. Or you can do a non-linear as well if that is needed. But having described that, we want to have a look at the accuracy, and that is adaptive multigrid with adaptive cases. The analysis of the accuracy we gain. Over here, let's assume if we have the comparison, that's not very helping. I'll go back, could I? Let's assume we are comparing the height of the droplet, and let's zoom in the very, very end, and hence this picture over here. On the top is a uniform mesh with 124 squared. The bottom is 512 squared. In the middle is adaptive multigrid, where the highest resolution, if refined everywhere, would be 124. And that is this what we call leaf nodes, as because grids are nested together. Leaf nodes we're saying the grid points the highest resolution grid points in that region, and that is the count of leaf nodes, and that is the accuracy we get. Clearly, it will have some compromise, will compromise the accuracy a bit if you're using adaptive. Why is that? Because the pressure. Even we resolve the moving contact length perfectly, the pressure, because we are coarsening in the middle and also other parts, there will be losing of accuracy in some ways in the system. But we say this, the height we get is much closer to the uniform mesh on the top, far away from the lower level of uniform, and we see that's acceptable accuracy. Also over here is a small table saying how adaptive time stepping works. And clearly works very well because it does reduce a lot of time steps in that case. And we're not really picking up a very small delta t to start with, just make it look good. The choice of the delta t for the fixed delta t, if we increase by a factor of 10, it will fail. So it is just because the problem-specific situation. We do have a table. It's telling pretty much the same story as this one, so I didn't include that. You can very well believe me on this. And also it was published, and not yet published, in this paper over here. Okay, brilliant. For the rest of the talk, we'll be on the optimal control with geometric evolution law for whole cell tracking. Chandrasekhar already gave a talk on how the model was derived in the conference that just ended last week before. The model is published in this paper, how it derives, and they got some examples with the cells. And we're currently writing up this paper. Submitted now is to do how do we solve this model efficiently, and also how do we solve that in 3D. We're also working on the ongoing model would be doing a 3D or more computational demanding cell situation to do the cell tracking, but you will see some results for that. The motivation and the objective is very straightforward. If you're giving two sets of image, and that's from time equal to 0, that's time equal to capital T, what we want to find is we're trying to find a forcing, so we can allows the morphology of the cell in this shape getting to the shape in the end, or desired shape over here. So that is really what we're trying to do, reconstructing the movements, and we really want to focus on reconstructing the morphology of the cell as well. The example, the image taken over here is from the French group publishing cytoskeleton. That later on we'll have a look at one of that movies. But before I move any further into the model equations, I think it's quite important to say what we are, because I think the mention of cell tracking is really open a can of worms. It's a lot of those techniques in there, and the people do it very differently. So where we are in all the tracking world, a lot of those you see from artificial intelligence or other companies, quite a lot of them to do is what we call the particle tracking. And it's not a cell tracking, not the whole cell tracking we're talking about over here. The particle tracking really is coming down if you're using the fluorescence to identify the cell nuclear. You've got those little dots lighting up, and you've got multiple cells, you've got multiple dots. You link the line between them and then tracking how the cell moves. But then this one, you definitely won't have the morphology of the cell. It's very hard to construct the cell with that kind of image as well. And also the tracking process is often flawed with automatic tracking and very slow with manual tracking. So we're trying to do something to improve this one. And the one we're doing is based on the pure geometric mass model, but the normal, the original model doesn't consider the shape as a cell. So from one shape to another, the shape can disappear and form another shape. And that's completely fine for them, but it won't be suitable for a cell setting because the cell won't disappear and reappear again. So that's what we're trying to do. The model is based on the model to conserve the mean curvature flow. It sounds as a capital gamma is the cell membrane. Eta is the forcing, where we're having this volume constraint term, which literally saying that is a cell, it won't disappear, we want approximates the cell volume over here. But clearly, even in 3D, I think it's probably a big assumption to say the volume would be conserved. And you can see the cell stretching out and comes back in. So it's just a constraint term instead of conservation. We take the phase field approximation of that equation, what Alan can. That's a Laplacian term. For the diffusion, we have a double well potential G prime, and that is the forcing counting and the volume conservation, giving as boundary condition. And the initial shape, phi 0, is the shape on the left-hand side. And then the final shape, the desired shape, is on the one on the right-hand side. And that gives the object functional. The first term is the term really assess how we are doing as a computed final shape against the final shape we have. And the second term is just to give a unique solution to this problem. And we want to minimize the objective functional. In the process, we have to have a joint equation just to help computing the derivative. That is a time-dependent p as a joint equation, but mind you, that p is going backwards from the final time to the initial time. And we update control using steep descent, using a steep descent update for the control. Before I go into discussion about the application of how this model, I think for me, I want to say is, as a computer scientist, how do we solve, what sort of procedure comes in to solve this problem? We have a forward phase field equation we want to solve. Let's say 100 time step for the sake of argument. How do we solve this equation for 100 time steps? But then we have to come back to solve this adjoint equation backward in time. And the adjoint equation depends on the solution from the corresponding time step of the phi. So that means if I have 100 time step of in the simulation, I have to store 100 solution of phi, just in order for this p to work. And then the p is depending. After that, we update the eta for all 100 time steps for every point, and then it depends on p, so we have to store p somehow for 100 time steps. And clearly, the choice of delta t do make a huge difference. Not only the computation you do, but also the memory you have to store in the computer. So they are two numerical challenges. The first of all is the number of time steps, because it does relate to how often or how much computation you have to do to solve the system. But memory requirements also is very huge. Considering we store the each solution using double precision, which would occupy 16 bits, 8 bytes of the memory, and let's use 100 time steps for the sake of argument, and then we can compute using a uniform grid how much memory would you require, and we compute with storing only 2 variables, because we don't really need to store 3, but we have to store either p or eta. And that's in 3D, it would really shouting out, because there is no PC that I know of be able to have that much memory allocation. There might be a few, they're stored in Pentagon, MI5, but you don't really see that in the market. And that is the reason we want to have a parallel computer, and we want to have designed some algorithm to actually reduce that amount, because that's a gigantic amount to do. And 512 squared in a 3D simulation isn't that fine. So the first thing we do is we're looking at the nature of the problem. If we have to come back again. That is semi-linear, but the adjoint equation is linear, and we're saying, well, we can resolve a linear equation really easily, relatively easily, on a coarse grid, right? And then we do the phase field on a fine grid. Also, it involves adaptivity if we wanted to. Hence, this two-grid solution strategy. We solve the Allen-Kern on a very fine grid. If we're using a multigrid, you can think about this recycle coming out like this. And then restrict the solution, and we only solve the adjoint equation on very coarse grid, and we only store all the information they required on this coarse grid, because that's why the Allen-Kern needed. Once we've done that, we can interpolate the solution obtained on the coarse grid back to the fine grid, because the linear equation, we hope we won't lose much of the efficiency. There is a big discussion, well, there was a part of the discussion in the paper about the accuracy of this, and I won't repeat that because I'm running out of time if I do. But you can very well trust me that we won't lose much of accuracy there. The difference for accuracy is about 10 to the minus 3 or 10 to the minus 4. So by using a two-grid solution strategy, we don't lose a lot of accuracy over there, but we have a lot to gain in the process. That is the end of the computation side of things. Now we're looking at a real-world example, and that is a video, 20 frames from the cytoskeleton, the French group published in there. Let's do the simulation. And now we're not only just going to do 2 frames, we're going to do 5 frames. And in order to achieve that, you're just having multiple adjoint states, and also you have to make the correct modification into the objective function as well, but it's doable. Let's take the first frame as the initial state, last frame as the desired state in the end, and we take the equivalent every 5 frames in between. So we got these 5 states. And we can do a simulation over here where you see the cell from one state moving to another state. It's not really looping, so I have to click it again. Or could I have to find? You do see the tail, the funny tail actually disappear off. Actually, this sort of like, because the the forcing is so great, and you got to actually left it over and then disappear. And that is something I think Shaker discussed in his talk. That we won't conserve the topology of this model, and there is a good reason why we're not doing it. But also it's a reason it's quite difficult to do it. Let's put it that way. But this may be something we can look at. One of those things could relate to a real close research collaboration between the mathematician and the biologist is you do have this forcing coming over, and this forcing, we can see it as the attraction force. And we know how large the cell is, also 20 micron from that image. And for one particular cell, it may be possible in the experiment to measure how much forcing a cell can get for a particular time interval or distance. And that could be something coming over here to say, well, if you get the forcing over that limit, it might be something not right. You can constrain that forcing to get for this for the experiment, and this could be something we do in the ongoing work, and of course could be something we do with the biologists. The second example. This is, sorry about the quality of the video, it's not great actually. It's a sub-region of original video. We've got 3 cells going on over here. It ignores one on the right-hand side. It's too close to the boundary. We can't really resolve it clearly. Cell proliferate, and that's the reason why I don't want to conserve the topology, because if we do, we won't have the proliferation going. The one on the, if I place it again, the one on the left will proliferate quite fast over here, where you get 2 daughter cells. And then those 2 will proliferate as the very last frame, or second last frame. And then you will have 6 cells in this simulation at the end of the time. And what this is reconstructed. There are 29 frames in this video. We put 10 time step between frames, so in total we have 290 frames, and that's exactly, you see the corresponding point. Oh, sorry, because I put the frame rate to be the same, so that's every frame is it's what it takes every time to get to the next frame, and it will move on. So that's the simulation we get to recreate the movement of a cell with relative to their morphology at every given time. And also what we wanted, and also quite a lot of biologists and people in the industry wanted, is to, if there will be something to tell us how many cells proliferated, hence you get a rate of proliferation. And it's something we bear in mind to actually do. We take this Euler number from Du's work published in Journal of Application Maths. That is a Euler number to compute, and A and B is the interfacial region of the phase field. So in our case, it would be between 1 and -1, and this is only exists in the interfacial region. We can compute this number as we go. So that is a plot coming out. They do have some wiggly lines over here. That's because the interfacial region, the resolution to the interfacial region might not be perfect, because the resolution over here is not too fine. It's only 320 squared as the grid. And we believe if we use a very fine grid, results the interfacial region much better. It should be a straight line over there, but a flat line over there. But the idea should be quite obvious. To start with 3, and that's the Euler number, tells you pretty much how many cells in that frame. So initially we got 3, and once it proliferated, it jumped up to 4, and in the end it will jump up to 6. I think this one will proliferate first, and this one will be only a little later, and that is indicated on the graph as well. That one's first, yeah. Then another one getting to near 6. So that is the Euler number. It is quite a nice indication of this, and we're thinking about to do maybe a bit more, a bit larger examples, and with a lot of cells in there. And also, I think it's something although we haven't really thought about the solutions, but I think it's something might come up into discussion, because you could say we can compute this number with a static image. We don't need to do the optimal control to reconstruct the movement. We can literally compute a number by giving the images. But there might be cases this won't work if you're considering a 2-image. Let's not make it let's not have the singularity over here, just to make it easy. So you have 2 images with 3 cells, and 1 cell is proliferated, and another 2 coming together, overlapped. If you calculate the Euler number, it should not going to tell you there will be a proliferation. And I did the simulation on this set of results, and it does come out having indication there will be 4 cells in the interval. So we do have the potential to solve some problems that can't be solved if you only look at static image. But the difficulty is, if you remember the funny tales in the beginning, we do have those false proliferation, let's put it that way. So of course a complete study needed to actually get rid of that one, to give real indication for the cell proliferation and not those funny tail detached from the cell. So it's not a complete solution, but has its potentials. And in the end, now I think I was 3 minutes over the time. I'll put a 3D example. Currently, we don't have a 3D cell image. I wouldn't stress it too much because there are 3D reconstructions for different kind of bone structures and all the networks. And I think other people are wondering why we haven't really got the cell description of the 3D. I can tell you it's quite difficult to get hold of any. We have a few, but only synthetic, and it just doesn't look very good. We heard about the technology they do is do this cutting, where you can have very good resolution on 2D, X and Y, but in that you could do 10 cut, maybe 20 cut, but then the resolution of that direction will look quite horrible. In a 3D representation of the 0 isosurface, you won't look at cell at all. You look some breaks moving through it. So that is something we're still in the market. If you know any data sets, I'm very happy to know. That is, but then what we're trying over here is that we can do 3D cell tracking with the morphology. We just put it again, and this is some synthetic data we come out and just to try and to see whether the algorithm works. And that is 0 isosurface you see for the phase field. Thank you very much. That's the end of the talk.
Questions?
Yes.
You said you're resolving the linear equation, the backward equation on the coarser grid.
Yes.
And how much coarser is the mesh? Can you quantify?
Yeah, I think that's a fair question. I think if we do that very precisely, we should actually have a study or somehow numerical analysis, say how coarse it can be. Of course, you want it as coarse. For this one, I think I just go probably about 3 or 4 level down. So if you have 124, you go to about 256 or 128, and that seems to do the job, and it seems haven't really compromised the accuracy that much. But I'm not sure. I couldn't really give you the answer if you go to like 64 squared or 32 squared. I'm not sure how much accuracy would be on that kind of grid.
It probably depends on which kind of information you need from the linear equation.
Exactly.
You only need an L2 information, so it's probably convergence. So
Maybe should be okay. Yes. Yes. I think you're right. We haven't really done any comparison for that. So we know we can take a much coarser grid, but we're not sure what the limits is there. So I think that's.
And then the other thing I would like to ask is, you mentioned in the beginning that explicit methods are
Yep.
completely different when you do parallelization.
Yes, they are.
And can you say a few words?
Sure. Explicit because it doesn't need a solver. First of all, that's the easy part. Without the solver, you don't do iterations. So you only would have a communication for the guard cell for every time step.
So, and you really only do also the Laplacian is then.
You only just do an update.
So
For yes, you save the trouble to implement the solver for the first place, and you also, by doing that, you reduce a lot of communication. But then again, if you're solving something like a very steep problem, you're forced to take a very small delta t, then of course, the communication will come up. But if you're not doing equation like that, explicitly in parallel is very competitive against the implicit method. Always implicit, because we are just assuming that the potential we're going to go to stiff problems and we're trying to evolve. I think if we maybe it's a bit hard to go back. If you remember that dendrite in the first 3 slides over there, well, in that research, because it is a fluid dynamics, it's quite easy. A lot of those measurements already published, so we have a chance to actually go compare the real world data, and that's what we did in their research. And it's actually very difficult to do that, and it's one of those numbers called Lewis number in certification, and that is it's a bit like this interfacial region. If the Lewis number goes very high, the interfacial region goes very narrow. To do with a real world example, you want the number to be 10 to the power of 6 or 7 to be able to start to compare. We can't really get to that with 1,000 core. We only get 10 to the power of 3 or nearly 4. So you need probably tens of thousands of cores to do the job. And that's why the reason why we're trying to solve the stiff problem, because we want to do the comparison. Same goes with the droplets. The droplets needs about 16,000 squared, because only 2D is only 2D model. You need a 16,000 squared grid to be able to start to compare. I think 40,000 squared grid would do the job to compare the real data. But those things have been done before, so that's in the literature. So there's a reason why you want to do the stiff, and then you want to use implicit method.
Also with the optimization, as Tim said, because you've got to store all the time steps from implicitly, you have to
Oh yes, that's also yes. Also, is another reason why we use implicit method for optimal controls, not only in the base field, but to reduce the time step seems it's a big gain for the efficiency solving this kind of optimal control model.
Any other questions? If not, we can